All right. Good morning. We'll pick up where we left off on Monday, and we're going to continue looking at what factors affect resolution and image quality and signal to noise and things like that in terms of the sampling and how you do that with CT. First discussion is about use of ChatGPT and Wolfram and MATLAB and things like that. If you use those resources for your problem sets, I'm fully on board with that, and that's fine. However, if you hand something in that has those resources embedded in it and with output and stuff, make sure it's really visible so the person who is looking at it, make sure you did the right thing. And also, I would say you need to put some commentary of your own as to why you believe the solution is true, and perhaps some comment on what it demonstrates in the context of that problem, right? So I don't have any problem with you using those resources, but if we get assignments that are handed in that are just output from that, it doesn't really tell you much about whether or not you've understood what is going on. So we're all working through how to use these resources. We'll work through it together and get to a steady state such that it's beneficial to you, beneficial to us, and everybody. So we started looking at image quality in the context of how data is obtained with computed tomography. And I just want to review a very simple notion of signal to noise. And that is, if we have an image in which the noise is uniform over the field of view, we can just draw a boundary or a region of interest, say, 100 by 100 pixels. So you have 10,000 estimates of signal level inside here. And let me put on the laser here, inside this region of interest. And you take the mean value over all those measurements, and you look at the standard deviation or the variance around that mean in that field. And that gives you an idea of the signal to noise. It's just the ratio of the signal divided by the noise, right? And then we looked also at contrast to noise, where you have two objects. You do that same thing, measure the variance in here and the mean, and take the difference between those two means and divide it by the variance as the contrast to noise. That's a simple definition of contrast to noise. And so when we're talking about noise and noise level, that's what we usually mean. This is a section of the textbook which, if you want to read this derivation, it's pretty illuminating. I'm not going to go through the whole thing. It would take about a half hour to go through the whole thing, but we'll just look at the results of this derivation. It's section 6.4.2 on pages 216 through 220, something like that. And so the question is, what are the factors that affect how much variance you get on your estimate of the Hounsfield unit in a CT image? And so remember, the Hounsfield unit is our estimate of the mu value for that material. And so Jerry Prince derives an expression. In the end, the expression we're working towards is, what is the variance of our estimate of mu, which is the linear attenuation coefficient, at a particular position in the image. So if I did this image 100 times and looked at the change in value that I estimate over those 100 times, what is that variance, right? And how is it affected by parameters involved in the acquisition? So the way he does it is he goes to a discrete version of back projection. And so our GL theta is written down as GIJ. It's just a 2D matrix. Instead of L and theta directions, we have I and J, okay, and they're discrete estimates. And just from our standard logging of the intensity measured over the intensity from the detector, your GL theta is proportional to that, to the logarithm of this ratio. And therefore, the variance in GL theta is proportional to 1 over this number here, okay? Given that, we write down an expression for the estimate of mu. This mu hat is our estimate of the mu value at a position in the plane xy. And then this is the discrete representation of the convolution back projection, right? So this is how we're going to do the convolution back projection on a computer when you have finite estimates. And the parameters involved here are this index j goes from 1 to m. And if we look in the formula here, this indexes our projection angle, okay? So this is the number of views or the number of angles. So let's suppose that the angles are separated by a constant delta theta. And so it's like the number of views that we've taken to obtain that image. And you can imagine you take 500 views, you take 1,000 views, something like that to acquire the image. And then this index, I, represents along the L direction, right? So these are our detectors enumerated from minus n over 2 to n over 2, and there's just an array of them, right? And so that index I runs along here. It gives us a position by multiplying by t, which is the detector separation. And so we've discussed this before, that for generations, the detector separation on a CT detector has been 1 millimeter, right? Just recently, Canon, when they were Toshiba, created a detector that cut that down to 0.5 millimeter in 2 directions, right? And we'll take a look at the consequences of that a bit later. But for all intents and purposes, most CT scanners, this detector separation is 1 millimeter, like that. So this function here of the line plus, this is basically the set of projections that we're going to back project. And this is the offset of those projections. Once we're at a specific angle, then we raster through I to get the projections along that direction. And we sum them up to get our convolution back projection. So this function is in effect, it's the ramp windowing plus the line selections, right? This C thing here. And so then Dr. Prince makes an assumption. So I'm just going to move this out of the way because I can't see it. There we go. Oh, there it goes. So, and that assumption is that the mean value that we're looking at a particular position, that this image has roughly equivalent values or similar values. So we don't have great oscillations in the amplitudes. And you say, well, that's not a realistic image, right? Every image has oscillations in amplitudes, otherwise there's nothing to look at, right? But what we're going to do is, if we go back to this example, here, in the background here, there isn't a heck of a lot of detail, but we do have a signal level, we do have a noise level, and we're computing what that noise level is as a function of changing parameters. So under that assumption, okay, and so now we're like on page 3 of this derivation at this point, we get this formula. And it's illuminating in that we have 4 variables here. The first one we'll look at is 1 over capital M, and we go back to this formula, and capital M, as we see here, is the number of views, right? So the variance on our signal is inversely proportional to the number of views, okay? So if I take an image with 500 projections, and 500 projections is sufficient to create a good sampling in a field of view, then if I divide that up and do 1,000 projections, right, really the only thing that happens is my variance drops linearly, right? It drops to 1/2 of what it was before. So it's basically just like averaging, right? So you're adding more projections in, and you average the noise down by dropping the variance, by increasing M, okay? It's linearly or 1 over dependence on N bar, which is basically the number of photons that we have detected at the detector, right? So how do I increase this number in order to decrease the variance in my estimate of what M bar is? I just increase the number of photons, right? So that's what this effect is telling us, right? Is that if you want to decrease your noise, you just turn up the current to increase the number of photons, and bar goes up and the variance goes down. That's sort of common sense in a way. It's also proportional. This is N bar divided by the width of the detector, right? So if you can also decrease your variance by increasing the width of your detector, right? As your detector gets smaller, then your variance is going to go up. That's those three. The killer is this one. And it's not in any of these equations here, but this, I don't even know what this letter is. This is the width of the ramp filter. Okay, the width and frequency space of the ramp filter. Okay, so remember, we looked at using that ramp filter to a certain frequency bandwidth and then cutting it off and saying that's it. And we'll do the inverse or the inversion of the data using that ramp filter. So this is an indication of how wide that ramp filter is. Okay, so the larger the width of that ramp filter, the more high frequencies we allow to get passed through the system. The less filtering of those high frequencies we've done. We haven't tamped them down. Not only that, because it's going up as a ramp, right? And this is in 2D, so it's actually a cone, right? If you rotate that around, you basically have a cone coming down to 0 at DC. Then as that cone gets bigger and bigger, the amount of noise, of high frequency noise that you emit goes up as the cube, right, of that width. And so as we open that ramp filter up, the noise, the variance starts shooting up very high, right? And so that's why everyone uses things like hamming, standard, as GE calls standard filters, to roll off those high frequencies, because this term starts to dominate your image and you get a very noisy image. So you get a lot of hash on the image, right? So those are the four big things we can change easily by acquiring data, right? Or those numbers. You can play around with these numbers with that iRadon MATLAB script that I gave you. You can just change, the nut. You can change M very easily, right? You can change N just by changing the signal to noise of the data, of the raw data. You can change the width of your ramp, etc., right? And see what the outcome is. We looked at that at the end of yesterday, so we can move along to our next lecture. Are there any questions about that? If you like, this is a pretty nice example or deep example of an electrical engineer getting hold of CT signal processing and deriving how the variance, what the variance is dependent on. It's a very nice derivation, not trivial to understand, but if you spent an hour or something in it, you could figure it out. So and we'll go to 8. So on lecture 8, here's this lecture from previous years, 20, 22. I'm not sure where 21, maybe it's there, maybe 21's there too. So if I get confused today and wander around, go back to those older lectures when I was younger. So here are these, again, a list of books that are really useful if you want to know about CT, and you can get them secondhand. They're all pretty old. So the question that has come up, was asked by the students was, well, how many projections do I need, through this object in order to create a reasonable picture, right? So, what is the separation between, if I take a readout and then move this and take a readout and move it, what's my spatial rate at which I have to sample that, right? So we looked at Nyquist sampling, right? The rate at which you have to sample digitally a signal in order to capture all the frequencies that are contained inside that signal. And so for us, it turns out to be, well, how many samples do I need across my detector? And then how many angles do I need to use to create an image? Obviously, 2 is not sufficient, right? 1,000,000 is way too many. So where is it? Like, what's the sweet spot there in terms of the number of angles that we're going to use? And the geometry that we're working with in the modern day for our problem right now that we're going to look at looks like this, right? In that we'll only look in 2D for analyzing this stuff. We're not going to look in 3D. And there'll be detectors that are separated by a constant separation, about 1 millimeter. And we'll decide how many angles to take with this source detector pair. In a modern scanner, in order to speed up the acquisition, they stack these detectors up to 256, 320 in the case of Canon. But it makes life slightly complicated in that the fan beam is going through the object at an angle, right? If you're on the edges here. So the projection that you detect on this last row of detectors here is at a fairly significant angle through the patient, instead of just being a straight line and, in the XY plane. We're going through in 3D. So you need to do some geometric adjustments in order to bring this cone beam geometry and to estimate what a parallel beam geometry would look like if you want to use standard convolution back projection. It's well worth the trouble, right? Because you can get an image now in 150 milliseconds that in these bad old days would take many, many heartbeats, many, many seconds to acquire. So let's look at, using that piece of code that I gave you, we can look at what undersampling produces. What does it look like, right? And so we'll say we start with a 256 squared image. That means in our GL space, I have 256 detectors along one axis, right? And we're going to make a 256 squared image. But I'm going to undersample. And that is, I'm only going to take 45 angles. They're evenly distributed between 0 and 180, but there's only 45 of them, right? So you can assume, like, we just don't have enough projections to fill in all of the numbers accurately in that background, right? So when I look at what the objects, this is the noise-free iRadon, inverse iRadon. So we're going back from 45 views of the actual object. So just to review what this does, in case you haven't played with it, it takes an object, which in this case are these dots, these little squares here, and it creates a GL theta space, which is quote unquote perfect. It's very high resolution. We then subsample that space. So I have, say, equivalent of, 1,000 views in that space, but I subsample those views such that I only take 45. I take that data that subsamples, invert it, do the inverse radon, assuming that I've only taken those angles, and then this image comes back. Doesn't look anything like the original, right? Because it's undersampled, right? So you can see that the characteristics are, we have all of these streaks, and these are those side bands. When you do the convolution back projection, you have, a function that's a bump, and then you do the convolution and it makes those negative side lobes. You back project that thing. And out here, we don't have enough of them back projected in order to cancel out these wings from the back projections, right? So this thing is giving us all of this artifact here. In some places, there's a higher density, and so things look a little better, but not much. And then when you add noise, right, to your data, this turns into this. So you still see there's structural artifact in the whole picture, right? That is evident even though you've got this noise on top of it. And in fact, the noise will give us a hint as to when the number of projections are sufficient, right? Because when we see that the noise gets better in its behavior, we can assume it's sufficient. So let's go up to 90 views. So now I have 90 angles along here. This is my L direction again. Oh, in fact, it looks like I have 360 detector elements along here. Sorry about that. It's not 256, 360. And then this is 90 views along here. The image is 256. And it changed, right? From here, 45 to 90. It changed, right? And so we got somewhat better behavior of the background pixels here in that we don't see these very structured streaks and artifacts in the background. And in fact, right around the center, it's starting to look like we're getting just a random noise field with a dot there. And just from a sort of common sense way of looking at this, you can imagine that for a very small object that's in the center, these projections that are going through it, perhaps 90 projections, are sufficient for the set of pixels that are really close to where all of those projections overlap, right? And we'll take a look at a diagram to explain this. So let's go to 180 views. And now we can see that there's a fairly large area that looks reasonable. There's still stuff out here that isn't behaving well. On the noise-free part, it looks like all of those sidebands have now started to cancel each other out almost completely in this area. But when we go farther out, we still have artifact, right? And then 360 views, it looks pretty good, right? In that all of those streaky things are gone, right? And let's just do 720. So this image didn't change much. This image, it does change, but can you see what the change is from here to here, right? 360, 720. So with 720, the only thing it changed is the noise went down, right? So just as that demonstrates that variance as a function of 1 over m went from 360 to 720, and the noise goes down, right? So it's just like averaging measurements together at that point. So question, can we figure out, is there a field of view inside which, if I only have 180 views, I can actually believe that the reconstruction is correct, right? Maybe inside this red circle, I do have enough projections to reconstruct pixels inside here. It's fairly clear that out here, I've got artifact and blurring and a whole bunch of weird stuff going on. In here, it looks pretty good. And so we zoom that up and say, okay, well, what's inside this disk? Why does this look different than the stuff out here, right? In this mode of reconstruction. So this is called view aliasing. And if we have a point here and we take our raw data projections like this, and then we convolve those projections with the Fourier transform or the inverse Fourier transform of the ramp function, right? So that function, I convolve these and I get these things, right? And I back project these four. Well, you can see there's a high density of estimates where they all overlap, right? There is a field of view inside which they're all overlapping. And you can imagine that as I add projections, that field of view, the core field of view in the middle will grow out, as I can add more projections, right? So here's from that same book. This is the classic 70s book, Kack and Slaney, where we have the number of projections on this axis, and we have the number of sample points in our detector on this axis, So this is the L direction, 64 points. Then I cut them in half, so I get 128. Then I cut them in half, I get 256. Cut them in half, I get 512, right? So I'm just adding more and more detectors and shrinking T by a factor of 2 each time, that width between the detectors. And so you can see a whole rogues gallery here of the interaction of resolution in the detector direction with number of projections, right? So let's start at the optimal, where we have a very high resolution detector, and I take 512 projections. Well, I get a pretty uniform background and an object in that background. And then as I move this way, right, such that I take fewer and fewer projections and I have lower resolution here, you can see that the artifacts start to abound outside a certain field of view, right? If I have a limited number of sample points on my detector, and I just continue to take more and more projections, you can see I don't necessarily get any better because this artifact structure is set by the fact that I've only got 64, but I do get rid of these streaks that are way out at the periphery. So my field of view goes out, but I still have a picture that is fundamentally limited by the number of lines that I'm projecting through it, right? So let's see how we can think about this to make a prediction of how many projections we need, okay? So remember, going back about 4 lectures, we talked about the Nyquist sampling theorem. And if we had a sinusoid that had a frequency of 1 cycle per millimeter, and here's 5 millimeters, and I plot that sinusoid at 1 cycle per millimeter, and here it's sampled every 1/10 of a millimeter, we put a sample down, and so we can see a very nice sinusoid. And remember, the Nyquist theorem was, well, what is the lowest sampling rate that I can use and still recover this sinusoid? And we found out that the lowest sampling rate was here. I needed a sample every basically 1/2 millimeter. And so I needed 2 samples per wavelength of that sinusoid, so that one was up, one was down, one was up, one was down. And so that's a Gestalt way of looking at the Nyquist criteria, like how many times do I have to sample? So what does that have to do with number of projections? Well, you can think of it this way, that there can be a match between the number of samples I have on my detector array. So in the L direction, if I have 1,000 individual 1 millimeter separated samples, and I want to make the correct number of projections for that 1,000, right? How are those two related? Here, we know we have 180 views have produced this picture, right? So that's fixed. So the question is, inside what diameter is that 180 views okay, right? And it turns out that this length along here, right, we want to have sample points along that arc, or an estimate at each point along that arc as we're rotating our sampling comb, right? And so if I have an arc way out here, I have many more sample points are required, right, to get a sample point per millimeter. If along my detector length, if I look at my detector and I have a sample every 1 millimeter, I basically want to sample every 1 millimeter along here, right? And so with 180 views, what does that allow this number of millimeters to be? Well, it's 108, pi d is the whole circle, right? So pi d over 2, we need that to be 180 points around here, right? And so it turns out to be a diameter of 115 pixels. Inside there, we have a match between our sampling rate on the L direction, the DL theta, and what my sampling rate is at a position or at an arc for 180 views, right? If I do 360 views, then I can go out farther and I will have enough to sample that arc with the same frequency, right? So let's look at that in terms of a diagram where we have the sampling spacing or the sampling frequency annotated. So here's my field of view in this direction. And I have a distance between each sample point on my detector. Say this is the vertical projection. And I have distance between each sample as delta L, right? When I decide on my delta theta, which is effectively deciding on the number of views, the number of projections that we're going to take, it's like, what is this delta theta? We can see as we go farther out in our field of view, the distance between the samples starts to become greater than the distance between the samples along the delta L direction as I go farther out. So the question is, like, where are they equal, right? So this distance from this sample to this sample, if I call it delta S, question is, at what radius does delta S equal delta L? And then that's a match between our sampling rate on the detector and the number of projections we want that are required to make a sampling density along this arc that is the same as the sampling density along this projection. Okay. And so therefore I can reconstruct a sufficient sampling inside that field of view. I'm going to go back to those artifacts in a second. And so algebraically, it works out to be very simple, right? In the sense that I'm given a delta L by my system. What I'm trying to figure out is what my delta theta should be, or delta S should be, in order to have sufficient sampling, right? I know that this distance along here, right, is pi FOV over 2, right? So FOV is my number of samples in this direction times delta L. So this should be N sub L would have been a better term for this. But the number of projection samples times delta L gives my field of view. The length of this line here is pi field of view over 2, just from simple geometry. So if I've got the field of views are equal, and I just say make these two equations equal, and then ask, well, when delta S equals delta L, what is the relationship? And the number of views that are required are pi times the number of projections divided by 2. And then you're set. And that's what we saw when we measured this, right? That's physically what it looks like inside when you have that number of views being sufficient. If you have an insufficient number of views, and we've already seen this with the artifacts that were in the examples above, right? You start to get a reasonable, looking image inside a subfield of view, but then after you get out of the, if you're in the undersampled region and you don't have enough projections, you will see these streaks coming off, right? If, on the other hand, you have an insufficient number of detectors along your detector element, right? So if we reduce those numbers, then the ability to place an edge at a specific location, right, gives you artifacts that come off of those edges, right, and spray back into the object. And so this artifact is classic when you see it coming off an edge. It's not far away from the edge. Over here, we're a long distance from the edge. This comes right off the side of the edge. And this artifact, if you move the object, a sub-pixel or sub-detector element back and forth, these artifacts will evolve in nature. They'll look look different depending on how much of a fraction of a detector you get. That's classic insufficient number of detectors for something that's really sharp. And noise will just give you random spray off of edges, right? I think, okay, did that. Okay, so we can look at the variation in images you just obtain on any old clinical scanner, and so the variation of signal to noise as a function of position in the field of view. And here in the center, we now know from this previous argument that we probably have the highest spatial resolution or the highest sampling of our object possible, right? Whereas out here, in order to do this reconstruction, we had to interpolate more between these points that were on rays that were divergent, right? And so it turns out when you look at the noise out here, we have a mean of 10 and a standard deviation of 55 in this region of interest. Inside here, there's a mean of 17 and a standard deviation of 69, right? And so these points seem to be noisier than do these. And that, I don't know if you can see this, but yeah, so you can also, I mean, appreciate the randomness or the level of noise by looking at different instances, independent instances of the image, right? So instead of just looking at how it changes in space, we can also ask, well, how, you know, the root mean square deviation in here, is it the same that I would get if I put a marker or a measurement on 1 pixel and took 100 images and then measured that standard deviation, right? But there's a few things that are dead obvious from this picture, right? The way this was obtained, this is a bit of a cheat in that this phantom is essentially constant in Z, which is going into the imaging plane here, right? And so we just look at images as a function of Z that are independent from each other as assumptions that they're replicants of each other in a statistical way, and look at the dynamics of how the noise is changing. And you can see that there's a lot of interesting radial artifacts going off at the periphery of the field of view. There aren't those radial artifacts here, but there is it's like a maelstrom of higher noise pixels in the middle, right? Yeah.
Can you expand a little bit more on why that's okay? Because like the better part of the image is one with more noise. That's
right.
Not...
Right. So it's a very good point. So the better part of the image often means you have higher frequencies available to reconstruct the object in that location without some artifactual spray coming off of the object. But that often comes with the extra bandwidth that creates just random noise, right? And so what is usually done, and reconstruction by vendors, and we're going to take a look at this in a little bit of detail, is different in the sense that they will regularize or smooth their data in their own way. And oftentimes, if you are in a position that is adequately sampled in your field of view, they'll lay off doing the smoothing, whereas when they go out to a position where they have to interpolate bigger distances between the actual data that's available, under those conditions, right, they'll smooth some more, right? And so you get this dependence in noise. And CT has this very interesting noise power spectrum. It looks like a ramp, right? If you use a ramp filter, it goes goes up like this. And so you get a lot more noise at these high frequencies than you do at DC. And it looks like they're occurring at this central zone here. So this picture, if you did it on 4 different vendor scanners, would look different, right? So they shouldn't really take away a general message about signal to noise here, other than the fact that it is darn obvious that it depends on spatial position in the image, right? So in CT, you can't really make a clean assumption that if I measure my signal to noise over here, that's the signal to noise for the entire field of view. That's usually not the case. Yeah, sure, go ahead. Right. Okay. So the same question gets asked again. It's like, why is the signals, why is the noise level higher in the central part of the image than, say, in the outer part of the image? And the simplest explanation would be that in the center part of the image, less interpolation needs to be done to the data in order to make the reconstruction, right? And so without that interpolation, the noise passes through, whereas with the interpolation to create the pixel values out here, the noise gets smoothed more, right? And we'll see as the signal to noise of the images changes, like the underlying raw data signal to noise changes, when you reconstruct it on a vendor's machine, usually the image just comes out blurrier as opposed to coming out noisier, right? Which is a little frustrating. And the reason of that for that is they look at the data and they say, you know what, we don't have enough data to produce an image with a signal to noise of 15. I'm going to smooth this data until I get an image that has a signal to noise of 15. And that's what they'll give you. We'll show some examples. Yeah.
That's for averaging. So you kind of produce you take a bunch of the same slice, average over and over.
Right. No, that's a really good question. And that is, in CT, does anyone ever do temporal averaging? And that is, if my noise is high, why don't I just take 2 acquisitions and average them together? And then my noise would go down by √2, right? The reason is because when you took your first acquisition, the equivalent way of doing that is just turn up the MA, right? So why not do that? And then you don't have any motion artifact or anything like that. So if I need to set my signal to noise, such as a higher level, usually I have enough juice in my X-ray tube just to turn up the X-ray tube. And that's the way I would reduce the noise level, right? And for the most part, most CT scanners, you can provide enough X-rays that you would always do that. And you would always reach a limit that is not scanner dependent, it's patient dependent. So you can always scan up to as much as you would want to radiate a person, right? And that's the job of the tube designer, is like, I'm going to give you enough X-rays, no matter what you want to do. If you want to make an image in 100 milliseconds, you will have enough X-rays to get that done, right? So that's usually what's done. Whereas in MR, you can't do that, right? You can't just turn up the polarization. It's like, oh, give me a factor of 10 in polarization. It just doesn't work, right? So you have to average to get the numbers. Okay, I'm going to try and turn down the lights a bit. This one. This one. Okay, yeah, because it's important to sort of see the subtle differences in these 3 pictures. So these are pictures from 3 vendors, and you can see they're of a human heart, not the same human heart, but basically pretty close. Contrast level pretty close in each one. Right? When I say contrast level, the amount of iodine contrast in the blood, the concentration at the moment this was taken. is about the same in each of these. This one might be a little bit higher by the looks of things, but roughly the same. The contrast is out of the right ventricle, so it has passed through and gone through the lungs and come back to the left ventricle. This is the descending aorta. This is the chest wall in each patient. This is the left ventricle, left ventricular muscle, left atrium, right ventricle is over here. Okay, so the patient, their chest is here. If they were wearing a medallion, it would be laying right here. Their left arm, as you can see, because the heart's on the left side of the body, is over here, and their right arm's over here. We're looking from their feet up to their head. So if you look at those, and I'm going to ask you a simple question, and that is, if you were to use one of these images to image the heart, just from the appearance of the image, which one would you choose? Which one do you like, right? So how many people, and everybody has to vote once, okay? How many people would like to read this image if they were going to do or they were asked a problem like, look for the coronary vessel. Is the coronary vessel open? And this is a coronary, this is a coronary, and that's a coronary, right? This is a coronary here, right? So who would like the left image? I've got 1, 2 people, 3 people want the left image. Okay, so those are the electrical engineers in the crowd. Who would take the middle image? 1, 2, 3, 4. Okay, who would take the right image? Okay, and some people didn't vote, but the right image wins. Okay, some people couldn't decide. They wouldn't take any of them, I guess. So though somebody who took the right image, why did you pick the right image? Anybody can say. Okay, so okay, perfect. So this edge here, this little, this is a valve leaflet coming down in here. It's a very thin object and it's imaged quite thin. This is a really sharp edge. If you look at the standard deviation of the signal in the background here, it's probably pretty small, right? The variation isn't that high. And so this is a vendor who does some amazing tricks in their reconstruction to make their pictures look like this, right? Who picked the middle image, and why'd you pick that one?
Average.
Okay, so it looked like, so you're saying it's smooth and there's probably less noise, saying it's just like, it looks like a very comfortable image, like it's nice and soft. It's got great contrast, right, between the myocardium and the background, right? Yeah. And then this one, so I think 3 of you, are you electrical engineers? Did you pick this one? And why? Okay, so best definition, and and that's probably true, right? When you look at this image versus this one, you would wonder what the definition is like in this one because it looks so smooth, right? It looks soft and smooth. This one looks a little raspy. It's got noise up there for all to see, right? And I'm assuming you say it looks like it has the best definition in that you probably believe the definition, right? Because it looks like the noise is out here. It's kind of the most honest image of the 3. And you can appreciate in this image like what the noise is, right? Like how much actual noise is there, as opposed to smoothing it out, right? So when you buy these systems, your head of CT or whatever basically looks at pictures that are coming from the system and bases their decision on which system they want, mostly based on how comfortable they are with the appearance of the image, right? And we've gone through a lot of development of what is the modulation transfer function of this scanner. Like, you know, which one of these three do you think has the highest modulation transfer function in that the greatest spatial frequencies are getting passed through? If you were to guess, how many people would say this one? Put up your hand. How many people would say this one? And how many people would say this one? Okay. Only like 6 people voted. How can we make a decision we don't have a quorum, right? We need a quorum. Okay.
But also, you know, how cost- if they give us the raw image, I feel like that's a better way of judging.
That's a
You're not giving us the raw image.
That is an excellent point. That's an excellent point. And that could be one reason to abstain from voting, because the question may be loaded, right? Or not important, because by the time they're finished with this image, Lord only knows what the point spread function is, right? Now you could test it on lots of phantoms and things like that to find that out. But
Also, is the resolution.
I think so. Basically, that most people use 512 pixels, and when you say resolution, it's displayed with the same pixel resolution. There's no difference there. Obviously, the resolution is different, right? This point spread function is wider, say, than this one, right? The way that's how this got there. So, but we had radiologists here. We bought this scanner, right? And we had a radiologist who's a very senior person, came from another place, came here and had worked with this scanner for years and years and never stopped complaining about these pictures, right? That person really wanted to go back to these pictures. They got to like them so much, right? And so in the lab, we took raw data from here and we said, well, look, it's just post-processing, right? We can make these pictures. I'll make it look like this. I said it with great confidence, actually, at the time. I said, oh, we'll just figure out how they do this. We went through like 10 different algorithms to try and make these pictures look like these ones, and we couldn't get there, right? And the weird thing about this picture is it kind of looks like an impressionist painting. You know, it's got broad brush strokes that are flat, and whoever this impressionist is does really nice edge work. They do really good lines, but it doesn't look like raw data. It doesn't look like something you get from raw data. So anyway, that's how this is done. There's a meeting called the RSNA where all of these CT manufacturers are there. It happens the week after Thanksgiving every year since 1968 or something. And half of all medical imaging sales happen at that meeting, right? Worldwide medical imaging sales. So this is a huge deal. 60,000 people go to this meeting. And all of the vendors have these pictures up on like their screen as to what, you know, the quality of their pictures look like from their latest machines. So let's look at image quality versus the number of photons, that n bar number in the equation that we had. This is a cardiac image that was taken over a whole heartbeat. So you trigger the scanner, you acquire data for the entire heartbeat, and then perhaps this heartbeat was a little shorter than expected. And so it kept acquiring data on the next heartbeat, but it was ramping the MA, the current down. So as the tube shut off, you know, the amount of X-rays goes down. And so there was still a window where the heart was in exactly the same position from one beat to the next. But in one case, we used 714 MA, that's the current in the tube, the X-ray tube. And in this one, 24 MA. So it doesn't really matter what 714 MA means, but their relative values mean something, right? So this is, you know, factor of, I don't know, what's that, 28 lower, right? So you still get a picture, right, with this many photons coming onto your detector. The signal to noise has not reduced by as much as the MA reduced, right? And so what happens in the black box that is the reconstruction unit on this machine, and it literally is a black box that sits by the scanner, it looked at the raw data and it said, you know, I can't go with this raw data, and it has to do some smart smoothing and interpolation and whatnot in the raw data space in order to create a picture that has reasonable signal to noise, and they sacrifice resolution, right? So if you wanted to know, like, does this person have a heart that is the right size? Is the muscle contracting, you know, in the right motion? What is the volume of blood in the left ventricle? All of those things you could measure from this data. If you wanted to ask the question, is this coronary vessel, which is the left anterior descending coronary vessel, is that thing open, right? And if it's open, you have this big bright signal here. We go over here and say, well, I have no idea, right? So this image just can't do that, right? It doesn't have the quality to do that. So depending on your task, you can acquire images with really low signal to noise, and they're still fine for things like this, you know?
Can you get like the actual raw data off the scan?
Yes, you can. However, there are a number of steps between what is raw data that comes off the scanner and what is the sinogram. And there are many steps, and one of them is the first thing they do is encode the raw data. It's not a tricky coding to break, but it's encoded, right? And so you have to get through that first, and then there's lots of bad pixels, and there's, you know, there's boundaries between the pixels that have lower sensitivity, so you need to normalize, you know, because when you look at the raw data from an object, as we did in some slides back there, you can see the detector elements and everything. So, but you can get it. There's a function that just says save raw data, and I'll do it. It was mostly for subsequent reconstructions. So if you want to save it, because this time next year they're going to have a recon algorithm that's way better, so we've saved raw data for a long time, and we have taken it back to the scanner and used their new deep learning reconstruction on that raw data and produced much better pictures, right? From years ago, right? They were collected years ago. Okay, so we'll look quickly at some image artifacts. And this same person, same slice, obvious huge difference in image quality. And what happened here was the tech or the patient or somebody got confused, and the patient had their arms down here and down here, right? And the arms are basically outside the field of view of the the shadow cast with the fan beam and the detector. So when the source is up here and we're casting a shadow on the detector, the arms aren't even in the field of view. And then when the source moves over to here and the detector's here, both arms are in the field of view. And so things are coming and going, you know, depending on the view angle. And that's not a good thing, right? So you get very inconsistent data in your back projection, and you get these streak artifacts that come off the object that is coming and going. You ask the patient to hold their arms up such that the only thing you're imaging is inside the field of view of the detector and the source shadow. And all those artifacts go away. So that's why when you get CT'd in your chest, your arms are always up here, right? You can see also that for these modern CT scans, where we have a detector that has many slices in Z, right? Remember that this is an exaggerated detector. This is a really thick, long detector, right? But it has, say, 320 slices in this direction. When the source projects through at this angle, we illuminate or cast a shadow from this part of the body. At 180 degrees, we cast a shadow from this, and they don't match, right? So unfortunately, we have to re-bin all of these views to get sort of a parallel recon model going. But it tells you that the true volume that you can trust with this CT, the true 3D volume, is this kind of football shape right here, right? So anything up here, over here, it's probably not going to be in view. You'll have to wait until you can move the patient into this. This is exaggerated. This geometry is exaggerated a bit. Okay. This is called, another artifact is called beam hardening. And we alluded to this when we were looking at the spectrum of energies that exist inside an X-ray beam produced by a diagnostic X-ray tube. And so if I set the voltage between the anode and the cathode to 120, right, kilovolts here, then this is called, this number of photons as a function of energy from 120 keV all the way down to 0. This is the relative number of photons that have been produced. You can see that they drop off to 0 at the low energy photons, and that is because we've put a piece of aluminum or we've put a piece of copper thin strip below the X-ray tube to get rid of those very low energy X-rays, because the only thing they would do is deposit ionizing radiation into the patient. They would not cast a shadow. All of these can cast a shadow, right? The interesting thing is that as that beam passes through the object or the patient, as I'm moving through there, I have a preferential absorption of the lower energy photons than the high energy photons, right? So the shape of this curve, you might know what it is when you enter the object, right? Because that's what came out of your tube. As it moves through the object, this curve tends to drop on this side. So the lower energy photons drop out and the high energy photons are still available. So when the X-ray beam hits this object, it is not the same incident density of photons, energy density of photons that hit the object when out here, right? So basically it's weighted towards high energies, and so the attenuation through here, might be lower than it would be if the object was over here. And that's what comes out. If I do a 180-degree projection and my photons come from this distance and they only travel this far before they hit this, then this same object will cause an attenuation that is different than it was when it went this way, because the incident energy profile is different. This is called beam hardening, right? So it's a depth-dependent change in the energy spectrum of the X-rays causes different amounts of absorption depending on where you are in the sample. Okay. So if you have a very uniform sample like this, and you image it without any compensation for beam hardening, the image pops up on the screen. It looks like this. And so this is one of the things, if you got your raw data and you just recon, you assume that I can just do a convolution back projection, and I do that, you're going to get an image that looks like this. Well, there'll be other artifacts in it, but this is one of the primary ones that'll be there, because you need to compensate for the fact that pixels in this region, before they see any X-ray at all, regardless of which projection angle that X-ray is coming from, that X-ray has gone through half the depth of this material, right? Whereas a pixel right here, when it sees it coming this way, it sees a lower radiation beam that has lower energies in it. And also when a projection this way, it has lower energy X-rays. And so it looks like it attenuates X-rays better out here than here. And the reason these look like they're attenuating better is they're attenuating different X-rays. They're attenuating X-rays that are, their average energy is lower than the X-rays being attenuated by these pixels. Okay, so that's called beam hardening. And this is called a cup artifact. And you can measure, for the spectrum of X-rays you've got, and you look at different thicknesses of water, you can measure what the effect of beam hardening is, right? You would get a graph that you predict, for a given thickness of water, if the energy was the same, you would predict what the attenuation would look like. However, what you find is you get less attenuation, right? Because the deeper you go in, the higher energy the photon beam is. And so you look at that curve, and that's your correction curve, right? For this beam hardening artifact. Okay, here's a few. We'll start getting into a couple of advanced applications. This CT has been shown without a doubt now after trials of, you know, tens of thousands of patients, that it actually is a survival benefit to have a low dose CT screening scan if you are a smoker over 50, right? So if you've smoked up to 50, 55, you should get a CT scan to look for lung nodules that are early stage cancer. Because when you take two groups and you don't CT half of them, and you let them, you know, you follow them for 20 years, and you take another group and you CT them and you treat cancers you find, and you follow that group for 20 years, the survival of the group that got the CT is higher, right? So your probability of survival is higher. And that's been now borne out. That was like a 25-year venture to prove that that was true, right? And so lung nodule screening, a screen means you're getting an image and you don't really have a symptom, right? You only have your life condition, right? So yeah, I'm a smoker and I'm 55, but I feel just fine. I don't have a symptom, so why would I go to the hospital at all? So screening means you image those people. They don't have symptoms. And what you look for are these little nodules here in the lung field, right? And they're hard to find. And as you can see for this one, right, this is the hardest of all these to find, because like it looks just the same as all this crap, right? All the vascular structure in the background. So when you look at how radiologists, human radiologists, perform at reading screening data, and screening data is hard to read, right? You get a lot of it and you have to do it quickly. You don't get reimbursed much for it. So 12 out of 13 radiologists picked up this nodule as positive, and it was a true positive nodule. 8 out of 12 radiologists picked up this one here. 5 out of 12 picked up this one, and only 2 out of 12 picked up this one, right? And maybe one of these 2 actually didn't pick up this, he picked up that, you know, you don't know. So this is a great application, obviously, for machines, right? So you really want to train a machine on 10 million of these pictures, and that exists, right? You have hospitals full of CTs, and you know outcomes of patients from their records that they did have a lung cancer or whatever. So you can go back, find the CT, know that that's a positive lesion, train, you know, put it into the training set, right? And so now you can be reading these, except your buddy is a machine that has read 1 million of them and can point to one and say, this is really suspect, this thing. You should pay attention to that one. And so that's how both screening for lung nodules and also mammogram screening is AI, and mammogram screening is a big application as well. You can imagine that AI in pathology. I don't know if any of you have watched how pathologists work, but my God, they're looking at huge fields of views of cells, looking for particular signs in these cells. And so again, that's a great thing for a machine to do that. So I think on the horizon, all of this will improve a lot as machines get better at being the primary screening doc. So here's a CT of a standard CT acquisition, right? And you look, and there's an obvious difference, right? It's sort of nature produced people that are symmetric, principally symmetric down the middle for radiologists, right? So they can look at the left side and the right side, and if they're different, then you've got a problem. And so if you look at this person's lung, it looks different over here than it does over here, right? And what you can do is there's a method of using dual energy X-ray to highlight the iodine concentration in an injection that you create. And so you can isolate the iodine itself and not the background water to determine sort of what is the concentration of blood flow in that region. And when you do that with this patient, this is called dual energy CT or multi-energy CT, you see that there's a big dropout in flow in this region of this lung versus this normal lung that has normal blood flow. And the way that's done is you basically take two CT images, and this is just for dual energy CT. You take one where your incident beam is set to 80 keV, and then you take an incident beam that's 140 keV, right? And so remember back almost to the first lecture or second lecture, this beam, because it has so many low energy photons, will be attenuated principally by the photoelectric effect. It's sort of a 50-50 photoelectric Compton, right? This beam, on the other hand, will have a much higher fraction that is Compton. In fact, it'll be like 95% of the interactions that attenuate these X-rays will be Compton. And so depending on the materials, you get a different ratio between the photoelectric and the Compton. And so, so for different concentrations of iodine, you know, basically intensity goes up with that iodine, but it goes up at a different slope than does, say, bone, and then does, say, water, right? So what you can do is with these two images, just algebraically combine the pictures such that it's equivalent to rotating this plane such that you zero out water. And then what you have left is, if it's a contrast agent that has iodine in it, it's just how much iodine is there, gives you the brightness. So it's like a concentration of an iodine picture, which for this application is obviously very useful, right? So looking at changing the resolution of the detector element, this is for GL theta, this is the L direction, right? So we've taken a standard conventional CT detector, and these are normally separated by 1 millimeter distances at the centers. And this vendor, this was a really gutsy move. They said, you know what, we'll just cut these. We'll make 4 detector elements for each one of these. And so this is what their detector element looks like. Gutsy move because there's a lot of data, you know, that has to be, a lot more data has to come off the scanner. Wasn't really clear that it would give you things that were valuable to see. But when you look at the pictures, it lives up to the expectation that if you change your sampling, so this is that T, right, or the width of the detector, the pictures get much better. And so here's a conventional image of this exact plane, and this is the super high resolution one. You can see certain features like these airways with even the wall of the airway that's highlighted, and that it just doesn't even show up here, right? And these 2 airways there with their individual walls of the airways. There's substructure in this little nodule that we don't appreciate over here. One catch, obviously, if you think and say, well, you know, what's going to affect my full width at half max? If you don't change your X-ray tube and it's still producing X-rays with a 1 millimeter spot size, right? Then just because your detector's higher resolution, you're not going to get higher resolution pictures because the X-rays are coming from still the same spot. So you have to make a new tube, and that tube has to have a spot sort of on the order of this size. That's a quarter of the area, and we're trying to get the same number of X-rays out of it, right? So that has to be a very special tube that can survive that kind of bombardment, you know. But they got that done. Principally, this scanner is really great for lean people, thin people, because, you know, you're going to be limited in the number of X-rays you can produce with something like that. But certainly shows a difference in spatial resolution, practical spatial resolution, not just phantoms and bars and full width at half max and all that. But, you know, this picture is a lot blurrier than this. What could have happened, and in some places in the body, you know, this and this might have looked the same because this just blurred through normal motion of physiology, right? Things in your body don't stay perfectly still for very long, right? So you have to, if you're going to image this thing, it has to be while that tissue is stationary, or the image has to be fast enough that it doesn't matter that the tissue is drifting, right? To make the image fast, you need a lot of photons, right? So again, it puts pressure on the people designing the X-ray tube. But it's pretty spectacular, right? The difference in detail there. And then here's that scanner used to image a human heart. And so we're going through these slices as we're pushing through this slice deck. This is an axial image. So we're going from, you know, the patient's head to, or heart towards, excuse me, feet towards their head, right? And you can see the ventricle coming into view here, coronary arteries here. There's a little piece of calcium in that coronary artery. Look at the valve plane here, beautifully high resolution. You can see the wall of the left atrium here, which is normally not highly visualized. A tiny little dot of calcium just went by there. Let me control this. We'll go back, take a look at it, because that's impressive. That thing there, right? Oops, my bad. That guy right there, right? So it works in the heart for somebody who is, look at their chest wall, very thin, right? They don't have a lot of tissue up front there, but really beautiful pictures. And here's an example, a direct comparison of a tiny spot of calcium in a coronary artery at this scanner that has the 0.5 millimeter separation. And then this is what it looks like on a regular scanner. This was a Canon, this was a Siemens. And you can see that it's very hard to resolve that there's actually a signal there on the Siemens. And this is partially because the slice has to be thicker on this scan on the right? So you're averaging stuff through a slice as well as getting resolution in plane. Okay, that's it. And okay, today, unfortunately, I have to go directly to get my daughter out of school. I get out early today. So I can shift my office hours to sometime tomorrow or Friday if you guys want to talk. But otherwise, we will see you on Monday. And Monday we'll look at some more CT applications.